The orifice tube with cycling clutch air conditioning system, referred to in this program as the OTCC system, is used on current models of the Vega and on C and K series light trucks. The OTCC system offers simple design and improved fuel economy, since the refrigerant compressor does not operate continuously. For this reason, there will be wider application of this system in future model years. In this program, we will review the operation of the OTCC system and some diagnostic procedures that are unique to it. The Vega and the C and K series light trucks use different control panels with some differences in air distribution. The operation of the system is governed by two levers and a switch located on the control panel. The upper lever is the selector lever, the lower lever is the temperature control lever, and the switch at the left controls the fan speed. The selector lever controls the compressor operation by means of a switch located at the rear of the control panel. When the selector lever is in either of the AC positions on the Vega, or in AC, bilevel, and defrost positions on C and K series light trucks, the compressor switch is closed. In all other positions, the compressor switch is open and the compressor cannot operate. The selector lever also directs air discharge in the vehicle from either the floor, dash, or defroster outlets. Movement of the lever varies the position of a sliding vacuum valve on the control assembly. The position of the valve directs vacuum to diaphragms that position the air doors and direct the airflow. Vacuum to operate the air doors is supplied by a vacuum reservoir in the engine compartment. A check valve located at the reservoir inlet prevents fluctuations in engine vacuum from affecting air door operation. The temperature lever is connected by a Bowden cable to an air door that directs air through or around the heater core in proportion to the lever position. In the hot position, all air is directed to the heater core. In the cold position, all of the air bypasses the heater core. The fan switch selects 4 blower speeds from low to high. There is no off position because the fan operates whenever the ignition switch is turned on. Only the high blower speed is provided when the system is recirculating inside air for maximum cooling. Now that you have an understanding of the controls, let's look at the operation of the system. The OTCC air conditioner functions on the same basic principles as the POA and VIR systems you are accustomed to working on. However, there are 2 major differences in the OTCC as compared to the other systems. First, let's consider the method of metering liquid refrigerant into the evaporator. In the POA and VIR systems, this is accomplished by a variable expansion valve that is sensitive to evaporator pressure and evaporator outlet temperature. The OTCC system employs a non-variable orifice called an expansion tube. This device is non-adjustable and must be replaced as a unit if it becomes restricted. The second major difference is the method used to prevent evaporator freeze-up. The POA and VIR systems utilize a suction throttling valve to regulate the minimum evaporator pressure so that its boiling point is never below freezing. The OTCC system uses a thermostatic switch to cut off the compressor clutch current when the temperature at the evaporator fins drops to near freezing. This stops the AC action until the evaporator fin temperature rises about 5 degrees. At that point, the switch deactivates and the compressor clutch re-engages. Here is a simplified diagram of the OTCC refrigeration system. Note that most of the components are the same as used in other systems and are serviced in the same way. High-pressure liquid refrigerant is metered into the evaporator by the expansion tube, where it becomes low-pressure liquid and begins to vaporize or boil. As the refrigerant boils, it absorbs heat from the air forced between the evaporator fins by the fan. The refrigerant leaves the evaporator as a cold vapor and liquid and passes into the accumulator. Here, the liquid settles so that only vapor is drawn into the compressor. A small bleed hole prevents compressor lubricating oil from collecting in the accumulator. The desiccant in the accumulator retains any moisture in the system. The compressor's job is to concentrate the heat picked up in the evaporator so that it can be discharged into the surrounding air at the condenser. It does this by compressing a large volume of relatively cold refrigerant into a small space. The temperature of the refrigerant is now hotter than the outside air, and heat will be given off into the atmosphere. As the high-pressure vapor gives up heat in the condenser, it changes into a high-pressure liquid and is delivered to the expansion tube for reuse. The expansion tube provides the resistance for the compressor to work against. The compressor is driven by a belt off the engine crankshaft through an electromagnetic clutch when current flows to the clutch coil. The entire refrigeration process is halted by interrupting the clutch current, which can be accomplished by any of three devices. First, there is the compressor switch at the heater and air conditioner control panel that must be closed for clutch current flow. Next, there is a thermostatic switch that cuts off compressor clutch current when the evaporator temperature drops to near freezing to prevent ice from forming on the evaporator tubes and fins. There are adjustable contacts in the switch that are held closed by a small bellows filled with a highly expansive gas. The bellows is connected to the tube that extends into the evaporator core. As the evaporator cools, the gas in the tube contracts, thus reducing the bellows pressure on the contacts. The contacts open and cut off the current to the compressor clutch. When the evaporator temperature rises about 5 degrees above the cutoff point, the contacts close and restore clutch current flow. Finally, there is a compressor discharge pressure switch located near the expansion tube that is pressure sensitive. When the switch senses low refrigerant pressure, it opens the circuit to the compressor clutch, thus shutting off the AC system and preventing damage to the compressor. Vegas are equipped with additional devices which will interrupt clutch current flow. A time delay relay working in combination with an AC relay is used on 74 models to prevent the compressor from operating for 20 to 25 seconds after the ignition switch is turned on, or when the selector lever is set at AC. This allows time for the vehicle's engine to stabilize before applying the compressor load to it. 1975 Vegas employ an AC control module that prevents compressor operation in the event the engine overheats. The module also prevents compressor engagement when the engine is cranking. Finally, a wide-open throttle cutout switch is employed to cut off clutch current when full engine power is required. Now that you are acquainted with the OTCC system and how it differs from other systems used in Chevrolet cars and light-duty trucks, let's look at some diagnostic procedures. Some preliminary checks that should be made when diagnosing an air conditioner complaint include drive belt tension, airflow through the condenser, and thermostatic fan clutch operation. Any one of these items can cause the air conditioner to operate below capacity. One of the first things a technician needs to know when diagnosing an AC complaint is whether the refrigeration portion of the system is operating properly. Since the OTCC system does not incorporate a sight glass, the following refrigerant quick check method can be used to determine if the system needs additional refrigerant. To use the refrigerant quick check procedure, first start the engine and wait for the thermostat to open. Then place the controls in position to achieve AC operation with outside air and high blower speed as shown. Note that the temperature lever on the truck control panel is moved to the detent just off the cold position. Leave the hood and doors open and run the engine at normal idle on the Vega or 1,000 RPM on C and K series light trucks. With the compressor clutch engaged, feel the liquid refrigerant line on the condenser side of the expansion tube. If it is cold, there is a restriction on the high side of the system, which will require that the system be purged and the restriction repaired. Look for a frost spot on the high pressure lines and condenser to locate the restriction. If the line is warm, next feel the evaporator inlet and outlet pipes while the compressor is engaged. If the system is delivering cooled air and the outlet pipe is approximately the same temperature as or slightly cooler than the inlet pipe, the system is properly charged and operating normally. If, however, the inlet pipe is cooler than the outlet pipe, check the system for leaks and repair any that are found. When this is the case, refrigerant should then be added 4 ounces at a time until both pipes are the same temperature. Then an additional 8 ounces should be added on Vega or 15 ounces on the light trucks. If adding refrigerant does not equalize the temperatures of the pipes, the system should be purged and the expansion tube checked for blockage. An important safety factor when working on refrigeration systems is the wearing of goggles. Remember that at atmospheric pressure, the temperature of liquid refrigerant is at least 20 degrees below zero. Should this cold liquid accidentally spray into the eyes, serious eye injury could result. In order to add refrigerant to the system while performing the refrigerant quick check test, use the following procedures with a portable charging station. With the engine off, remove the caps from the gauge line fittings on the vehicle. The high-pressure fitting is located in the high-pressure liquid line opposite the compressor discharge pressure switch. The low-pressure fitting is located on the accumulator. Close all the valves on the charging station and connect the high-pressure line to the high-pressure fitting. Purge the pressure gauge hoses of air and moisture by opening the high-pressure control valve and cracking the low-pressure control valve. Allow refrigerant gas to hiss from the low-pressure line for 3 seconds. Next, connect the low-pressure line to the low-pressure fitting. Close the high-pressure valve and open the low-pressure valve. Start the engine and engage the compressor in order to draw refrigerant into the system. Open the refrigerant control valve and allow refrigerant to enter the system. As we have noted, the refrigerant should be added 4 ounces at a time after performing the refrigerant quick check test. Remember, though, that a restriction in the system, as well as a low refrigerant charge, can cause the evaporator inlet pipe to be cooler than the outlet pipe. Therefore, when adding refrigerant, the high-pressure gauge should be observed to prevent a dangerously high buildup of head pressure. If the temperatures of the inlet and outlet pipes do not equalize when adding refrigerant, or an excessive pressure is observed on the high side pressure gauge, the system must be purged and the expansion tube checked for blockage. When removing the gauge lines from the fittings after charging, be sure to keep your face clear of the refrigerant discharge from the hose. Now let's review the refrigerant quick check procedures we've just completed. Remember that the purpose of the test is to provide a rapid means of determining if the refrigeration portion of the AC system is operating properly. The key to the test is that when the refrigerant charge is adequate and the system components are operating properly, the inlet and outlet pipes of the evaporator will be approximately the same temperature or slightly cooler at the outlet. The additional steps outlined and the use of the charging station are only needed when the system fails the quick test and it is determined that the problem is a lack of refrigerant, a leak, or a restriction in the system. Now let's look at some complaints involving malfunctions in the compressor clutch electrical system of a 1974 Vega. Take a few moments to examine the diagram. Here's a 1974 Vega that does not deliver cooled air from the AC outlets. The owner stated that the system worked fine the day before, but does not function now. The first step in diagnosing a problem of inadequate or no cooling from the AC system is to verify the complaint. Position the AC controls to achieve maximum cooling with a high blower speed. Turn the ignition switch to the run position and listen for the click of the compressor clutch and the sound of the blower fan. Remember, since this is a 1974 Vega you are working on, you must wait at least 25 seconds for the clutch coil to engage. In this case, the blower works, but the compressor clutch does not engage. Since the blower and the compressor clutch are wired to the same fuse at the fuse block, the trouble cannot be a blown fuse. We have determined so far that there must be an electrical system malfunction somewhere in the clutch circuit between the fuse block and the clutch ground connection. Let's follow the technician as he continues the diagnosis of the clutch circuit. The technician next checks the electrical connections at the compressor clutch coil and also the clutch ground. They too check out okay. He then connects one end of a jumper wire to the positive side of the battery. With the other end of the jumper clipped to a small screwdriver, he contacts the hot side of the clutch through the back of the electrical connector. An audible click indicates that the clutch is engaging. If the clutch does not engage, the clutch coil is defective and must be replaced. In this case, the clutch engages and the malfunction lies somewhere else. The technician next checks the compressor discharge pressure switch by attaching a jumper wire across the terminals of the switch connector. If the clutch engages, the switch is defective, or the system is low on refrigerant. To determine if the system is in need of charging, the refrigerant quick check procedure can be used with the jumper wire still in place. In this case, the clutch did not engage when the switch was jumpered across, indicating that the malfunction is somewhere else. The technician continues his diagnosis. He attaches a jumper wire across the terminals of the thermostatic switch connector. If the clutch engages, the malfunction is in the thermostatic switch. Since the clutch does not engage, the technician continues his diagnosis. Keep in mind that on C and K series light trucks, the test procedure would move from the thermostatic switch to the compressor clutch switch at the control panel. However, since he is working on a 1974 Vega, the technician next tests the throttle cutoff switch in the same manner as he tested the thermostatic switch. The clutch does not engage, indicating the switch is not the problem. He then tests the time delay relay by removing its electrical connector. If all other components are functioning properly, the clutch should engage when this connector is removed. Here, the clutch does not engage, so the technician reinstalls the connector and proceeds to the AC relay. To test the AC relay, he connects a jumper between the terminals of the two 16-gauge wires in the connector. This time, the clutch engages, indicating that the AC relay is malfunctioning. If the clutch had not engaged, the one remaining component he would have had to check would be the compressor clutch switch on the back of the control panel. The compressor clutch switch is tested by connecting a jumper across its terminals. If the clutch engages, the switch must be replaced. Now let's briefly review the steps that the technician followed to find the malfunction in the compressor clutch circuit. First, he determined that the fuse was not blown, since the blower operated off the same fuse. He next found that the clutch functioned normally when energized directly from the battery. Because the remainder of the circuit is like a chain, he bypassed each of the components, one at a time, until he found the broken link at the AC relay. The one exception was the time delay relay. Its function is to hold the AC relay open for 20 to 25 seconds, and he tested it simply by removing its connector. In the rare event that two or more components are defective at the same time, it would not be possible to locate the problem by bypassing each component as we have outlined. In this case, it would be necessary to use a test light to trace the voltage from the fuse block to the first open point in the circuit. Once this open has been corrected, the circuit is checked further until the second defective component is located. Here we have a service situation in which the vehicle owner complained of a metallic scraping sound in the engine compartment when the air conditioner was turned on. He also indicated that the air conditioner output was low. The preliminary checks revealed that the compressor drive belt was properly adjusted, but the compressor clutch was slipping or not completely engaged when the clutch electrical circuit was energized. From this, you know that the problem is in the electrical circuit to the clutch. Let's follow the steps you would take to diagnose this clutch problem. If you are working on a 1974 Vega, the next step would be to check the time delay relay. To do this, remove the relay connector. If the compressor clutch engages normally, the relay is poorly grounded or is malfunctioning. To check for a poor ground at the relay, you would connect a jumper wire to the relay bracket and to a good ground and reinstall the relay connector. If the compressor clutch engaged normally after 25 seconds, with the relay connector installed and with the jumper wire in place, the relay would have to be removed and the ground connection cleaned. If the compressor still chattered or slipped with the relay grounded and the connector in place, but engaged normally with the connector removed, the malfunctioning relay would have to be replaced. In this case, the compressor clutch still chatters or slips with the time delay relay disconnected. So next, test for proper voltage across the compressor clutch coil. With the system operating on AC and high blower speed, the voltage across the clutch should be at least 11.5 volts. If this voltage is present and the clutch is chattering or only partially engaged, then the clutch or clutch coil is defective. In this case, the voltage reads below 11.5 volts. So next, check the system voltage by connecting the voltmeter between ground and the ground side of the AC fuse. If the system voltage is below 12.8 volts, you will have to troubleshoot the charging system. In this case, proper system voltage is present, so you will have to check each component in the clutch circuit until you find the one causing the low voltage at the clutch. With the current flowing through the circuit, that is, with the clutch engaged, no component should register a voltage drop greater than 1/2 volt. This is done by connecting the voltmeter across each component while the electrical connector remains intact. When testing the AC relay on a 1974 Vega, which here has been unmounted from the evaporator case cover, connect the meter to the two 16-gauge wires. In this case, the relay shows a voltage drop of 1.5 volts, indicating it is the cause of the low voltage at the clutch. From this you know that it will have to be replaced. Remember that all voltage dropped across the components in the compressor clutch circuit reduces the voltage available to operate the clutch by an equal amount. Now let's examine the compressor clutch circuit on the 1975 Vega. As you can see from this diagram, the current flow in the circuit is quite different from the 1974 model. Note that in the 1975 system, the time delay and the AC relay have been replaced by an AC control module. The AC control module provides a 2 to 5 second time delay of compressor clutch engagement and also prevents clutch operation while cranking or when the engine overheats. A function check of the AC control module can be made on the bench using a fully charged 12-volt battery, 4 jumper leads, and a test light. To test the module on the bench, first connect jumper wires from the battery negative terminal to the terminals marked 3 and 5 on the diagram. Next, connect a test light from the battery negative terminal to the terminal marked number 2. Now connect a jumper wire from the positive battery terminal to the number 1 module terminal. After a time delay of about 2 to 5 seconds, the test light should glow, indicating correct module operation at this point. Next, connect an additional jumper wire from the battery negative terminal to terminal 4 at the module. The test light should go off, indicating the engine overheat shutoff is working. Disconnect the jumper from terminal 4 and the test light should glow again after a 2 to 5 second delay. Now disconnect the jumper from terminal 3 and the test light should go out. Reconnect the jumper to terminal 3 and the test light should relight. If the AC control module fails to function as described in these test steps, the module is malfunctioning and will have to be replaced. The information we have covered in this program will provide you with the knowledge to diagnose most problems related to the OTCC air conditioner. Additional information contained in your update reminder booklet includes troubleshooting guides, performance test procedures, and performance data. Keep this reminder booklet handy for your reference when servicing the OTCC air conditioning system.